Let's talk about Yang. Now, quite honestly, Yang can be one of those pretty confusing topics, and one of the big reasons for this are all the little quirks and changes between different Yang models, I find. So what do I mean by different Yang models? Well, within Yang we have three different styles of model. The first type of model you're going to see is the IETF model. The second one is one called Open Config models. And the third is called native models. But in this nugget, to start us off, what we're going to look at is the IETF models, so let's talk about them. Okay, so the IETF, we've all heard this acronym before. This is the Internet Engineering Task Force. And the whole purpose of the IETF, generally speaking, is that it's an internet standards body. And what they're really responsible for is the development of things like protocols and standards. Now really the IETF is a really big international group of operators and network designers and researchers and vendors and more. Now the whole purpose of this group is really to improve the internet. But as you can imagine, improving the internet is a very large task. So here's the thing, to actually combat this overwhelming problem of improving the internet, the IETF is actually subdivided into different areas. Now one of these areas is called the Yang Model Coordination Group, and what they're focused on is developing Yang. No surprise there. Now the key factor within the IETF Yang models is that these are open standard models. So you know the way OSPF is an open standard routing protocol, whereas something like EIGRP would be proprietary. The IETF is focused on creating models much more like the OSPF that are not dependent on a vendor. Simply put, the core purpose here is to be able to model our network devices, where we don't need to worry about interacting with different vendors, because they're all modelled the exact same way. So the goal here ultimately is that you model your entire network based on these IETF Yang models. Okay, so here's the thing, within Yang we have this concept of configuration data and state data, otherwise known as operational data. So configuration data would be like if you're going to configure OSPF on a device and you typed router OSPF1. That would fall under the configuration part of the model. But if you wanted to verify that your OSPF was up and running and you did a show IP OSPF neighbor, that CLI show command is really just getting you the operational state, i.e. is the adjacency up or not. Now clearly both of these concepts are very, very important. We want to be able to use configuration to make changes on the devices, but we also really want to be able to verify our changes have taken place correctly. So it's really important that both of these concepts are taken into account when we use Yang. Now here is the problem. Trying to combine the configuration and operational data within a Yang model kinda proved to be pretty difficult. Now ultimately many different options were considered, but originally the IETF decided that the best way to proceed was to distinctly model the configuration and operational values separately. So all your config would indicate what you want to happen to the device, the desired state of the device, and the operational is simply going to indicate whether the current value is what it should be. So let me take an example here. In the original IETF interfaces Yang model, you would have a container simply called interfaces. And on the same level within the tree, you're also going to have another container called interfaces-state. Now the big advantage of using this type of model, at least in my view, is that to visually inspect the Yang tree, it's pretty easy to separate out this data, because it's so distinctly and cleanly partitioned. But there are some issues, the first of which is that you're having to provide multiple parallel lists for everything really. So there's a duplication in the Yang data model which can be redundant in many cases. We saw the example for interfaces, we've got two containers and two lists for interfaces and interfaces state. But you don't just have two separate containers and two separate lists for interfaces, you've also got to model the keys twice. And in the case of interfaces, the interfaces type is also modelled twice. Now clearly this is not the most optimal solution in the terms of efficiency. Here's a second issue. It's actually pretty difficult to navigate between the two from a programmatic point of view. Consider this. Let's say you made a change to interface gigabit 1. So what you would do would be to go into the interfaces container Again, it's going to be interfaces and not interface state because we're making a configuration change. And say you selected an interface. So interface name is equal to. So you make this change to this interface, and what do you automatically want to do immediately after? Well, you want to verify that this change has taken place and taken place correctly as you expected. So how would you actually do that? Well, you might be thinking it's an obvious answer, and to you and I, it probably is an obvious answer. What you would do would be to change this container to interfaces state. So that seems like a fairly simple solution. The problem is, it's easy for you and I as humans to denote this. In our brains, we just switch out the values. Thing is, to actually have computers do this, it does become pretty cumbersome. What you have to do is manually map all of these containers together. So the IETF thought, wouldn't it be better if we could have this knowledge just built into the protocol, so that this type of information was automatically discoverable? And this is where the big change within the IETF happened. So to understand this change, we need to talk about the protocol netconf. So netconf has this concept of data stores. So the first data store we have is the startup data store. The second is the running data store. And the third is the candidate data store. Now, we don't need to dive into too much detail in this nugget on these concepts, but roughly speaking, all this is a place to have your startup configuration, a place to hold your running configuration, and a potential candidate configuration. Now, the IETF got to thinking that if we want to be able to elegantly handle this concept of having configuration data as well as operational data, and we don't want to always have to split the tree and have constant duplication, the best way to solve this would be to introduce two new data stores. So now we would also have an intended data store as well as an operational data store. And these two new additions comprise of what is now known as the Network Management Data Store Architecture, otherwise known as NMDA. So within the concept of the NMDA, we still have the running data store, just as before. Now the running data store is going to hold a complete current configuration of what is on the device, just like when you do a show run on the CLI. Now this running data store can be read and it can be written to, you can change it as well. Now here's the thing, with the intended data store, this data store is a read-only configuration, cannot be written to, so changes to the device will still be made to the running data store. Now whether that's if you write to it directly, or if you target the candidate data store and load it into running afterwards. Either which way, the intended data store is only going to be a read-only representation of the running data store. Now you might think, what even is the point of this? Well, realistically, in very basic servers, it's going to contain pretty much the exact same information as the running. But in more advanced servers, you can also have additional information in this read-only data store, such as templates and inactive commented out configurations. So the other new kid on the block is the operational data store. Now you might be tempted to think that this holds just all the operational information, just the state data. That was certainly my intuition when I first heard about this data store. But here's the thing, it's a read-only data store, but the schema of the operational data store contains all configuration as well as all state data. So that means if we have config set to true within the Yang model, or if config is set to false, both of which are going to be present within the operational data store. So how is this relevant at all to the splitting of the configuration data and the state data? Well, here's the thing, instead of modeling the configuration and operational data completely separately, by using this new network management data store architecture, now the IETF could have a single unified model. Now you don't actually get the state data or the configuration data depending on the containers you specify. Instead, if you want just configuration data, for example, you would just target the intended data store and that would split apart from the operational state. So let me just briefly show you how this actually changed the look of the Yang model within the IETF. So if I go into the Yang models, which I've downloaded, I do an ls and I go into standards, ls again, and then into IETF. So let's go into RFCs. Now if we do an ls, we're going to see a bunch of all these different Yang models. So let me just focus in on the interfaces, so I'll grep for interfaces. Okay, so we have a 2004 model and a 2008 model. Now you're going to see the differences in the way these models are now implemented. Let's first look at the original, the 2004 version. So I'll just copy this, and I'll say PyYang, paste this in, and hit enter. And there we have the original IETF interfaces Yang model. Now look at the actual structure we've got here. At the top of the model we have two split containers. We have the interfaces container, and then down here we have the interfaces state. So if you want to make a change to a description on an interface, well, that would be a configuration change. So you would go into the interfaces container, and then you would specify the interface you want to go into within the list, and then the description. And what you're going to notice is that within the interfaces container, everything is read-write, because it's all writable data. However, if we go below and go into the interfaces state container, all of this is all state data, completely separated. And you'll notice that everything is read-only. Absolutely everything. So a very clear distinction in the tree. So how does things look in the new model then? So let's grab the 2008 reworked version to include the NMDA. So PyYang F3. Now as this Yang model unwraps, at first glance here, you see the interface's state container, and you're thinking, John, you told me this was now gone. Why do we still have this container and all of this read-only data? Well, here's the thing, all of this is actually deprecated. But one of the things, a big thing within the IETF in Yang, is that they always want to maintain backwards compatibility. So here's the thing, if a device does not support the new NMDA architecture, if it doesn't have an intended data store and an operational data store, you can still fall back and use the interface's state container. And quite frankly, on many modern devices, you're still going to have to use this technique. You'll still need to use this container. But let's go up to the configuration container. And really this is where the new model lies. It's all under the interfaces container. So we don't have to always duplicate information. The way we split this information is just by targeting different data stores. And if we go to RFC 8343, we're going to see information about this change. So if you do a search for RFC 8343, let's check out this interface update. Now this RFC has a ton of information, but really the summary of changes tells you what you need to know. The interface's state subtree, that container, with all the config false, all the read-only data, that's now been deprecated. All your configuration false, i.e. all your read-only data, is now present just within the interfaces subtree within the interfaces container. Now the reason why I'm pointing all of this out again is because this part at the bottom here, some servers which don't implement this new architecture where you can just target these new data stores, they may still implement the old deprecated interface state tree. So if perhaps maybe you're using a Cisco device and you want to be looking at operational data, if you can't target the operational data store because it isn't actually implemented, the way you would get around that would be going the old outdated way and targeting the interface's state container. And this is what I was highlighting at the start of this nugget, that all these little changes, all these little quirks depending on the device and the Yang model can be a little difficult to navigate. It does take time, it does take practice. But from the highest level view, the most important thing to remember is that IETF is an open standards body concerned with making Yang models that are open standard. So the key emphasis here is having interoperability between different vendors. Now here's the thing, the IETF isn't the only open standard attempt at making Yang models. In fact, we have another one called OpenConfig. And it's the OpenConfig Yang models that we're going to be exploring in the very next nugget. So I hope this has been informative for you, and I'd like to thank you for viewing. In the previous nugget, we had just discussed the IETF, and the whole purpose of these models was to give us an open standard data model. Now here's the thing, the pretty weird thing is that we also have another open standard implementation of Yang, and that is by a group called the OpenConfig group. So if we already have the IETF, which is giving us open standard models, why on earth do we need another open standard model to give us more open standard models? Okay, here, so the philosophy is similar but different. when we're talking about the IETF are very, very rigorous, could you say? And quite honestly, it takes a lot of time for them to be able to develop these models. It seems, at least from my vantage point, that they really must pour a lot of effort and a lot of time into developing these models, because quite frankly, they don't come out very often. Very, very roughly speaking, the IETF seem to want to perfect things before they're released. So that's obviously a good thing in one sense, it's very robust. You can expect high stability using IETF models. Now the problem is though, is that if you're going to spend so much time into developing a single model, then it's going to be pretty hard to be able to model absolutely everything for every possible network configuration. And this is kind of what the open config people noticed. So who are these mysterious people known as the open config? Really, the open config group is an informal gathering of network operators. Now the project was originally started by this small company called Google. Might have heard of them. Google were the ones who spearheaded the way. But this grew to become a rather big collaboration between Google, BT, AT&T, and another small corporation called Microsoft. Now these operators, these group of people, they had a kind of shared vision. They liked the idea of this open standard, model-driven programmability, but they really wanted it to be implemented at a faster rate. Quite frankly, the open config group were pretty frustrated, it seems. In their eyes, the Yang models were just not being produced fast enough. Another problem they saw was that the IETF were a little bit too restrictive. So what do I mean too restrictive? Well, the IETF were adamant that they were going to follow the RFC strictly, and that was that a new Yang model version can only introduce backward compatible changes. So if you recall from the previous nugget, even though the IETF had remodeled the interface's Yang model, all of those changes, no matter how radical they were still backward compatible. They still had the routing state container for devices which did not have the ability to follow the MMDA. So obviously this is positive in a sense, it's very, very good for backwards compatibility, clearly. But the open config group had this vision of model-driven programmability based on open standards that were not locked into a vendor, but there would be a focus on faster releases and more flexibility. And this is much more in line with the kind of typical software development. Anyone who knows software development knows that it's not a very good idea to try to perfect your software and then finally have this grand release where there's going to be no bugs, no problems, no revisions. Instead, what software engineers and software developers tend to do is iterate and make corrections as they go along. This is much more closer to the philosophy of the open config approach to Yang. So what you actually notice using open config models versus the IETF is that the open config has much better feature coverage than the IETF. They get the models out faster, and whilst they're not as strict as the IETF, you can expect pretty reasonable stability. Now previously when discussing the IETF, we discussed their philosophy of breaking the Yang tree at the roots. If you had an interfaces container, that would have config, and interfaces state would have your state. Or if you had a routing container, you would also have an adjacent routing state container. So there was a very clean partition and separation here. We briefly examined those benefits and some of the drawbacks, and the drawbacks were deemed strong enough to actually make the IETF reconsider and remodel their whole strategy. So that whilst they still have the interfaces state container, it's in a deprecated form purely for backwards compatibility. And instead now, the new models follow the NMDA. So what does the open config do? Do they split the tree? Or perhaps they rely on the data stores of the NMDA? Well, the truth is they actually have their own convention. So instead of having two separate lists for configuration and for state, open config kind of blends config and state throughout the tree. Basically, you can expect a single list and then a config branch, and below it, a state branch. And this just happens recursively as you go deeper and deeper into the tree. So this solves the issue from a programmatic point of view, in that we can use the same container. It's not going to be interfaces and then interfaces state. We would still just use the interfaces container. And within that, you're going to have items which have the config flag set to true or the config flag set to false. But it does have some drawbacks. Personally for myself, I find it a little bit harder to read, just visually as a human. It's not clearly separated, it's more blended. So let's see what an open config model looks like then, shall we? Okay, so let's look at an open config model. So we'll say ls and we'll grep for open config. And let's just look for interfaces, let's grep for that too. Okay, so we'll grab this. We'll do pyang f3 and paste this. So you see here at the root of the tree we have our interfaces container, and within that we have an interface list. Now here's what I say when it's all blended. We have config stuff here, which is all of this, and then we have state, which is all of this stuff going all the way down here. And what you'll notice is that state actually is a superset of config. So if you see it in config, you're going to see it in state, but not everything you see in state is going to be present in config. So we have config name, config type, state type. And this is true for MTU, loopback mode, description enabled, MTU, loopback mode, description enabled. Now this still might look like the IETF original model, but let's just scroll down a little bit, shall we? Notice that this pattern keeps recurring no matter how nested the data becomes. It's not a clean split with two containers at the root of the tree, it's going right through the tree, blended right through it. So for hold time, we have config and states. Similarly, we go to the sub-interfaces container, we have the sub-interface list, and as you can see, we have config, and then below that, the states blended right through. And as you can see, config has index, description, and enabled, and state is the superset. It has index, description, and enabled, as well as all of this read-only operational data. Let's quickly examine another one. So we'll do ls, and we'll grep for open config, and we'll also grep for network. And what I'll say is pyang f3 open config network instance .yang. So you're going to have to excuse the ugly line wrapping we've got here. This model is a lot larger, but I just want to highlight the nested nature of this. So as we can see, right throughout the tree we have config branch, state branch. If we go into MAC addresses, we have config branch and a state branch. And again, notice that state is a superset of config. Config has MAC address and VLAN, state has MAC address and VLAN, plus also some additional ones which are not present in config. If we scroll all the way down, again we've got config state for encapsulation, config state, and now as we get much more nested we go to the endpoints container, again config and state. And this goes right throughout the tree. So programmatically this works pretty well, but as you can see it's a little bit harder to see on the eyes. Whereas with the IETF, the original way they had effectively a config container and effectively a state container, and they were totally partitioned, they went off in different directions. Basically you would open the Yang model and you'd take a left to go to config and take a right to go to state, and you would be on your own separate path, very clearly split. Whereas with open config, even though we do have a config and a state option, but the difference is what you can expect to see when you examine an open config Yang model is that this concept of config and state is going to be deeply intertwined all the way throughout the entire model. So to briefly recap, OpenConfig attempts to solve a similar problem. They're focused on having open standards. It doesn't matter if you've got a Juniper device, an Arista device, a Cisco device. Using these Yang models, you can model your configuration the exact same way independent of the vendor. This is obviously very good programmatically, you don't have to change any of the logic within your scripts. Now OpenConfig had a focus on releasing models faster and with more flexibility. So a byproduct of that is that you have better feature coverage because they could iterate quicker and get them out faster. But perhaps they're maybe not going to be quite as stable as the rigorous IETF. Now here's the thing with open standards, they try to cover the broad cases and they do a fairly good job at that, especially OpenConfig. They have very good feature coverage of general configurations. That said, you can still buy a device and expect to get particular features that are just native to that device. So there is a third Yang model we're going to explore, and that is the native model. And it's this model that we're going to be looking at in the very next nugget, so I hope this has been informative for you, and I'd like to thank you for viewing. Okay, so we've arrived at the third of our three Yang models. So far we've seen the IETF as well as OpenConfig. Both of these were developed around open standards and interoperability between vendors. The third one is a little bit different, and this is our native Yang model. So a native Yang model is really just a proprietary Yang model. It's native to the vendor. So who have native Yang models? Well, for a start we have Cisco, as well as other vendors such as Juniper and say Nokia. All of these vendors want to be able to implement truly feature-rich model-driven programmability, and quite frankly for some cases the open standards just don't cut it. They don't have the coverage. Now the opposite is true in the case of our native models. Your Cisco native model is not going to be interoperable with your Juniper native model because they're going to be completely different. But let's say you maybe wanted to implement a layer 3 VPN and you had a lot of very specific configuration you had to carry out. It might transpire that the IETF or OpenConfig don't cover the features you need. In this case, you're going to be using the native Yang models. Okay, so a question I'm sometimes personally asked about native models, which I would just like to clear up, is that if you have a Cisco native model, does that apply broadly to all devices? Like, is there just a Cisco native? Well, the answer is no. Cisco has native models for NXOS, its Nexus platform. It has native models for its iOS XE platform, as well as its iOS XR platform. Now personally, I really do enjoy using the native models because I enjoy the feature-rich functionality, but quite honestly there still are some niggling problems with these models, and these are things you're going to have to consider if you're going to implement native models within your network. Okay, so straight off the bat, the one big win you get here is feature coverage. Pretty much most things you can configure are covered by the native models. Now the price you're paying for that is the fact that you're not going to have consistency across your network if you're using different vendors. So clearly, lack of consistency is not a virtue. Now the problem I have with the Cisco native models is that there even is consistency within the different models. So what do I mean? Well, very often it seems like there is very little regard for this idea of backwards compatibility. So this was something that was a great focus of the IETF. The IETF want that if you happen to use a model from 2014, and if you have a script tailored for that 2014 model, it should still work on the 2018 updated model. This is a big win for me. In the native models, there isn't that kind of stability in my opinion. So let me just give you a fairly recent example. So pretty recently I built a script called Yang Getter, and it's on the Cisco DevNet Code Exchange. Now the purpose of this script was that a user could open up this script and just enter a single keyword to pull the particular Yang model or the feature of the Yang model that you want to see. So if you wanted to get the OSPF configuration, you would just type the word OSPF, and effectively under the hood the Yang Getter script was going to abstract away those details and pull that model. Now the problem is, this worked fine for a little while, and then randomly in one of the updates, Cisco changed the native Yang model. And it was one of those changes which brings no real value to the Yang model. It was just a change. So previously the OSPF container was just called OSPF, and the logic of the script was to target this OSPF container, but then randomly what Cisco did was switch this up to router OSPF. Now this doesn't actually improve any functionality of the model, all it's really doing is breaking backwards compatibility. The same thing happened with the EIGRP container. EIGRP became router EIGRP. So then maybe logically you might think that the BGP one would become router BGP, but randomly Cisco decided to keep this one as it was, but just change the other two. These are just some of the quirks you're going to have to deal with in model-driven programmability. And in my opinion, I've seen a lot more of this dealing with native models than with the IETF. Network automation, what can I say? Sometimes it's like the wild, wild west. Okay, so with the native models, this is not the only inconsistency you're going to see. Take for example the Cisco iOS XE models. So with the Cisco iOS XE devices, we have a native model. And within this model, you're going to have absolutely everything with respect to configuration. So this is a really good way to get the configuration off the box if you don't know where to look. If you just pull the native Yang model, it's going to pull back all configuration. Now when I first started automating Cisco iOS XR, I wasn't quite as familiar with it as with iOS XE. So I was trying to find the same type of model. I was looking for an iOS XR version of native.yang. That way I could effectively pull the running configuration off the box and see it all in its Yang structure. But with Cisco iOS XR, there is no native Yang model, at least at the time of this recording. Perhaps that'll change. So the architecture of the Cisco iOS XE is that we do have this concept of the root container. This would be native, and from that you're going to have multiple containers spidering off of this container, but this is the one that's going to unify everything. So maybe you might have a container which has interfaces, you might have a container which is router, and from router you would have OSPF, or now that's been changed to router OSPF, and maybe a container with NTP. so on and so forth, but effectively the point is that every container stretched back home and touched the native container, all built from that container. This was the root of the tree, so to speak. And there actually is some functional use of having this native container which ties everything together when you're using the RESTconf protocol. But that's a conversation for another day. Suffice to say though, I think this native container is a very good idea. But the problem is that in iOS XR, it doesn't exist. So iOS XR, you would maybe have an iOS XR interfaces model, and from that container you'd have all these other containers spidering out, and then you would also have maybe a BGP model, so you'd have the root container just saying BGP, and then you'd have more information just spidering out, and then maybe a XR NTP model. And just like the others, you would have containers and leafs and lists just spidering out. But crucially, all these models, all these containers here, would not be unified by one root container called native. Now this concept of native doesn't exist in the IETF or in OpenConfig, so it's not like by using Cisco iOS XR native models you're losing some type of feature functionality which you have in the open models. All I'm highlighting here is the inconsistency across the different native platforms. So what I'm really highlighting here is that the Cisco native models, even though they're under the same company, don't expect uniformity across the different platforms. Just be aware that when you're using a native model, you're going to get a lot of features, but you also might experience inconsistency not just across vendors, but even with different platforms of the same vendor. The models themselves will be different, and even the general way you navigate those models are going to be slightly different, just due to these differing architectures and conventions. Now, with respect to this config and state problem, how does Cisco solve this? Well, Cisco is much more like the original IETF where they split the model. The difference here is that Cisco literally split the model. It's not split at the root. We don't have an interfaces container and an interfaces state container. Instead, we have two very distinct and separate Yang models. So if you were looking to configure interfaces in the case of iOS XE, you would get a model called something like Cisco iOS XE. I can't remember if this is exactly the way it goes. But then it would end with interfaces.yang. And if you wanted the operational state of the interfaces, then it's going to be Cisco interfaces oper. Two totally different Yang models. So operational state, these are the models you would use for your streaming telemetry. And the case of just configuring interfaces, maybe configuring a loopback, you would just use interfaces.yang. Now with iOS XR, it's kind of the same but a little bit different. The model convention is going to be that when you have operational data, it's still going to have this -oper, but again, for whatever reason that Cisco have decided, but when you have a Cisco iOS XR configuration Yang model, what you're actually going to see in it is cfg.yang. So let's look at these models and see how they actually look in real life. Okay, so let's do cd yang. This time we'll go into the vendors, we'll choose Cisco, and we'll go into our XE models. So let's choose revision 1721, whatever, do an ls. So if I do an ls and I get for say NTP, you can see that we have two models here, one called ntp.yang and the other called ntp-oper.yang. So the bottom one here is our configuration. Let's open this one up. And as you can see, we've got a bunch of read-write stuff because this is writable data, configuration data. And if we want the equivalent of our show commands for our NTP to verify our NTP configuration, well, we would go to a completely separate Yang model. Let's grab the Opera one this time. And you'll notice that inside this model, it's all read-only. Everywhere read-only. So the IETF originally split the Yang model at the root. You had an interfaces container and an interfaces state container. Cisco in this case kind of followed the same type of path by splitting all this data, but they just didn't split it within the same Yang model. They put configuration and put state in totally separate models altogether. Now this may be not the best solution programmatically, but for me as a human, I do find it a lot easier to be able to find the information that I want to find. Now let's look at the XR data. So we'll go into cdxr. Let's go into maybe 721 ls. Let's maybe do the same again. We'll get it for NTP. Now, like I said, for configuration data within XR, you're going to see this CFG. And just like with XE, for operational data, it's going to be -oper. So quickly, let's just look in here and see our configuration data. So copy this, we'll do a pyang f3, paste this in. And as you can see, we've just got all this read-write data because this is all configuration. And just as before with the XE model, for operational, we'll just change this to oper. .yang, and effectively we're going to get all of our state or show commands here. So to summarise, really what you have to remember with the native models is that they are native and unique to the vendor. The positives is you're going to get a lot of feature coverage, whereas the downside you're going to lack vendor interoperability, so you have a lack of consistency. Now anecdotally from me, I've noticed that the native models are a little bit more gung-ho when not adhering to backwards compatibility rules. So be aware they might not be as strict as the IETF, and also be aware that even though native models are from the same vendor, they might actually differ, and in fact do differ between particular platforms. And those are the main differences and similarities between the three different types of Yang models. We have the IETF, the OpenConfig, and the native models. So I hope this has been informative for you, and I'd like to thank you for viewing. Now that we understand the kind of Yang models we can expect to see on the device, our IETF, our OpenConfig and our native models, let's explore how we can find out which models specifically are supported on a device. And the way we're going to achieve this is send a request to get the server capabilities. And the device we're going to test is going to be the Cisco iOS XE Always On Sandbox. That way, if you want to follow along, then you can do so. So the first thing we need to find out are the credentials to log into this device. So let's go and grab them. So the very first thing which I'm going to do is Google DevNet Sandbox, and we'll click this top link here. Okay, so let's get started with Sandbox. So I'm just going to log in with my GitHub account. So the sandbox that I'm going to search for is the Cisco iOS XE Always On device. But there are other options here. If you want to use the Cisco iOS XR device, then search for that instead. So I'll search for XE. And I don't want to have to reserve a box. I just want the one that is always on. So let's click this one. And all I'm looking for here is the login credentials. So it tells me here that the credentials are Cisco iOS XE latest one cisco.com. Now I'm going to log in over netconf, which means I'm going to use port 830. The username is going to be developer, and the password is going to be Cisco12345 with a 1 as the I. So remember those details, we're going to use them in a script. Okay, so the first thing I'm going to do is create a new directory, and I'll just call this capabilities test. You can call it anything we want. And I'll just cd into this new directory. Now, in order to send a netconf request, what I'm going to use is the Scrapplay library. In particular, we're going to use Scrapplay netconf. So for good hygiene, I'm going to install this into a Python virtual environment. So let's do that first then. So what I'll say is Python 3 m for module, and then I'll say ven for virtual environment. Then all I'm going to do is specify a dot, which means create the virtual environment within this directory, and hit enter. Okay, now let's activate this virtual environment. We'll say source bin activate. And now we have activated the virtual environment. So let's install Scrapplay netconf. So what I'll say is Python 3 m for module, and I'll pip install Scrapplay netconf. Okay, so if I do pip freeze and I get it for Scrapplay, that automatically installs Scrapplay as well as we get Scrapplay netconf. So we're ready to go. Let's write this script then, shall we? Okay, so clear U. So let's call this script test.py because I'm super original. So the very first thing we want to do is say from Scrapplay netconf, and we're looking for a driver. What I'm looking to import is netconf scrape. Now let's create a simple Python dictionary with those login credentials for the always on sandbox. So we'll just call this device, and we'll use our curly brace. Now the first option we're going to give it is host. So then we give it the host, so we'll just paste this in, then we'll add a comma at the end and give it a new value. So what we next want to specify is the username. So we'll say auth underscore username, and the username is going to be developer. We'll specify the auth password, which we know to be Cisco12345 with a 1 for the I, and another comma for a new key value pair. And we'll say auth strict key. This is a simple lab environment, so we'll just say false. And the last key value pair is going to be port, and the netconf port is going to be 830. And let's just close the curly brace. So now we have our Python dictionary with all the key value pairs we need. So let's create a new variable called connection, and we'll take our netconf scrape import, and what we want to do is unpack the dictionary, so we do that with 2 stars, and then the name of the dictionary, which is device. So we'll do a connection.open, And the next thing we want to do is send a request for server capabilities, but we also want to print the output. So the first thing I'll do is create a variable called output, and that is going to be contingent on using our connection variable. And the method we're going to use is server underscore capabilities. This is going to instruct Scraply netconf to send that request to retrieve the server capabilities. This is going to give us our list of all the supported models on the device. So lastly, we'll just print the output. So let's save this and run the script. So we'll say python 3 test.py. And there we have a Python list of all of the supported models. Now if you're like me, this is pretty difficult to read. So I'm going to make the output a little bit prettier by installing the rich library. So I'll say python 3 pip install rich. And let's go back into our script. And let's add an additional import. So what we'll say is from rich, what we want to do is import the print function, and we'll import it as rprint. Now all I'm going to do is go down to the bottom here and change the Python print function to rprint, which is going to use the rich library instead. So let's save this and rerun the script. python 3 test.py. And this is actually a much more readable version. So let's just scroll up a little bit. So just through quickly eyeballing this result, we can see we've got our native models, things like iOS XE AAA, and this is an Opera model. We've got models for ACLs for BGP, and if we scroll on down, we can see we also have our OpenConfig models, things such as LLDP and Network Instance. And if we scroll on down further, we also see we have IETF models. So for example, the IETF interfaces model. So the capabilities don't actually tell us what's currently on the box, it just tells us what the device supports. So you might see an AAA model within server capabilities. That doesn't mean that AAA is configured on the device, rather that the device has the ability to support that model. Now if we just want to see all the configuration on the device and their corresponding Yang models, what we can do is send a netconf getConfig. And again, we can send this request using the Scraply netconf library. So let's do that then. So let's copy our original script, test.py, and we'll create a new one called test2.py. So we're still going to use netconf scrape, we're still going to use the same dictionary because we have the same credentials targeting the same device. We still want to unpack that dictionary and open a connection. The difference here is that we don't want to use the server capabilities method, we want to use the getConfig method. So let's change this up then, and we'll say getConfig, and we're also going to add a source data store. So the data store we're going to target is the running configuration. So we use the running data store. Let's save this, and we'll run the script, test2.py. And all I got was a successful response. Let me make a slight amendment here. What I'll need to do is use the .result attribute to get the actual text back. So I'll say .result. So what I say is python 3 test2.py. And what we're going to see is the full configuration with all the models and all the namespaces. Now quite honestly, this is a fire hose of information. It can be a little bit hard to read. So sometimes if you've got a rough idea of what you want to look for, you can maybe add a grep filter to bring this volume down a little bit. So perhaps maybe I was looking for OSPF, I could grep for OSPF. And so for example, the namespace we're using here actually tells us the Yang model for Cisco iOS XE OSPF. And this would be the model we could use to configure OSPF. So using getConfig is a really good way to get all the configuration off the box. And if you want to see something in particular, say something that is not in the box, I would just recommend going in via the CLI, say for example configuring BGP, then running a new getConfig which is going to pull back all the information on the box and either scan through it manually or begin to use some grep filtering. Okie doke, so server capabilities. This shows us the models which are supported on the device, and if we want to see what is configured on the device, we can send a getConfig. And both of these features are very useful when working with Yang. So I hope this has been informative for you, and I'd like to thank you for viewing. So throughout this skill, we've seen the different types of Yang models available to us. We have IETF, OpenConfig, and the native models. We've also seen some techniques to be able to find out which models are supported on which devices. So naturally, you might be thinking, what model do I use? Well, just like so much of network design, the answer is, it depends. Generally speaking, it's probably a good idea to try to implement an open standard. This really is the dream scenario. if you can make it work, because then we have consistency and uniformity throughout the network. You can use the same logic to parse out the same information between devices, because that information is structured the very same way. However, as you can probably tell, sometimes this is just not an option. If you're implementing some really advanced features, then the chances are you're not going to be able to do this, in which case you're going to be looking to the native models. If, for example, you're implementing EIGRP within your network, well, you're going to be using a Cisco native model. But very broadly speaking, very generally speaking, I would say that if you have a fairly simple network, then the IETF models might be a good choice for you. However, realistically, I've found that the models for the IETF are just a little bit too bare to be able to implement any real production network. Generally speaking, for open standards, OpenConfig is likely a better choice. It's going to be vendor neutral and you're still going to get quite a lot of features. So very broadly speaking, out of the two open standards, I would think that OpenConfig is likely the best bet for most scenarios. In fact, overall, on the balance of things, it's probably the best overall choice in most cases. Again, with a big caveat, open models are going to be limited. Now, a question I'm sometimes asked is, what about a pick and mix? You know, a mix and match. Now this is possible to do. You can use an IETF model for your interfaces, and perhaps a native or an OpenConfig model for another feature of the network. But generally speaking, it's probably best avoided. That said, if you're going to implement this type of mix and match approach, then make sure the mix and match is from different features. You don't want to be using the native model and the OpenConfig model for network interfaces, for example. If you do this, you're probably asking for trouble and are going to experience a lot of unforeseen and unexpected events. So let's look at a quick script to see the advantage of using an open standard model, in this case OpenConfig. Okay, now in this quick example, what I'm going to be using is the Python automation framework called Nornir. Now you really don't have to concern yourself with the details of this framework. All we're focusing on here is the general implementation of the OpenConfig Yang model. So with Nornir we have the concept of an inventory. So if I go into my host.yaml file, what I've populated this inventory with are 3 devices. And these 3 devices are for the Cisco IOS always on sandboxes. And I have the credentials for the Nexus device, always on, with the username and password and the ports. Same for the Cisco IOS XE, which we saw earlier. And I've also got a third device, the always-on iOS XR. So if I was going to connect to these devices, I could use a Cisco native model. But like I say, we don't just have a general model for Cisco. The native models are actually split up by platform. So if I wanted to use the native models, I would need to reference 3 different models for each device. I'd need to reference an NXOS native model, an iOS XE native model, as well as an iOS XR. Now instead of using 3 different models, what I'm going to do is just reference the one model, and that is going to be an OpenConfig model, which is an open standard which should work on all 3 devices. So let's look at the script then. So the script is called example1.py. Now again, you don't have to concern yourself with the intricacies of the Nornir framework. All we're doing here is telling Nornir where our configuration file is, and then telling Nornir to use the Scraply library we just saw. But the beauty of Nornir is that we're not going to connect to each device sequentially, we're going to connect to every device at the exact same time, so it's much faster. But here is the real important part that we're focusing on. So what I'm going to do is send a netconf get request to all 3 devices, the NXOS, the iOS XE and the XR. And I'm going to use a netconf sub-tree filter, this is called. In this case, I just want to pull the OpenConfig interfaces, and I'm using this sub-tree filter to be even more granular, to specify even more specific data. So for example, to pull out the counters, the in unicast packets to the interface, as well as things like the operational state, is the interface up or down. But the key point to note here, the main thing I'm trying to focus on, is that because we're using OpenConfig, well then this filter is the exact same for all 3 devices. It doesn't change. And here's the thing, if I was connecting to 3 more devices, let's say a Nokia device, a Juniper device and an Arista device, this filter, because it's an OpenConfig one, would be the exact same for all 6 devices, rather than having to craft a special snowflake filter for every single one individually. so it keeps our scripts much more compact and much easier to create. So let's send off this subtree filter and retrieve this information from all 3 different platforms. So I'll do a Python 3 example1.py, and there we have it. We've pulled back the information. Here we have the NXOS device and all the information here, and if we scroll up a little bit, we also have the information for the iOS XR device, and scroll up yet again, we're going to see the information for the Cisco iOS XE device, things like its name, description, operational state, which is up in the case of Gigabit Ethernet 1, and the in unicast packets is 109,890. And like I say, the logic was the exact same across all 3 platforms. And this really is a big advantage of using the open config models. So general rule, where possible, try to use open standards, but if you must, you can also fall back on the native to get additional features, but really try to limit a mixing and matching of both open config, IETF and native models. But if you must implement them both, really refrain from implementing both models on the same feature, because quite frankly, it's going to give you a lot of headaches. Okie dokes, I hope this has been informative for you, and I'd like to thank you for viewing.